Hello everyone, I'm Ruotong Wang from Xi'an University. I'm very glad to present our work here. In this talk, I will present TransVPR, a transformer-based place recognition model with multi-level attention aggregation. Visual place recognition is a challenging problem in autonomous driving and robot localization systems. It can be defined as a large-scale image retrieval problem. Given a query image, the algorithm has to determine whether it is taken from a place already seen and identify the corresponding images from a database. There are two types of image representations in VPR tasks, namely global features and patch-level descriptors. Global features are used to retrieve top-N candidates from the database, and patch-level descriptors are used to perform cross-matching to re-rank these candidates. One specific challenge of place recognition is that there are always many distracting elements and dynamic objects in the scene, such as vehicles, pedestrians, cyclists, trees, and the sky. They cause confusion and occlusion and thus seriously harm the VPR performance. So, how can we avoid the impact of these distracting elements? This involves the attention mechanism and is exactly what our model solves. To this end, we propose TransVPR, a transformer-based VPR model which adaptively selects distinctive image regions based on multi-level attentions. It simultaneously extracts robust global and patch-level image representations. Besides, the model can be trained end-to-end with only image-level supervision. Now let's introduce the details of our model. Given an input image, we firstly extract its patch-level features from multiple convolutional feature maps. The concatenation of the representations of each patch is embedded as raw patch descriptors. Then, these descriptors are sent to a transformer encoder to integrate global contextual information. Next, three groups of output patch tokens from the low-level, mid-level, and high-level layers of the transformer are selected and concatenated. Three different attention maps are generated and then merged. The diversity of the three attention maps can be learned by interacting with different patch token size in the next step. Finally, a global image representation for each level is generated by weighted summing the patch tokens using corresponding attention maps. Then, they are combined to obtain the output global feature. The merged attention map is further used to select the key patch descriptors. The whole model is trained end-to-end by supervising the output global features using triplet merger laws. Now we move to the part of experimental results. By observing the model performance when using different combinations of attention masks, we can validate the idea of aggregating multi-level attentions. Furthermore, the effectiveness of the proposed attention aggregation strategy is demonstrated by comparing with some degenerated versions. We evaluated our model on several public benchmarks and compared against some state-of-the-art methods. Our approach conventionally outperforms all compared methods on Mapillary and Norland datasets with a large margin, and it also achieves competitive results on Pittsburgh and robot car datasets. In addition, because computational time and storage requirements are also important considerations for real-world applications, our model achieves a superior trade-off between accuracy and efficiency in both terms of latency and memory. We present here some retrieval and matching results for the proposed model in various challenging conditions. We also visualize the attention maps learned by our model. Attention maps from different levels tend to focus on areas with different semantic information. By aggregating these different visual cues, we can finally determine which image region is in fact useful for place recognition. That's all for my presentation. Thank you for listening. If you have any questions, please feel free to contact me. Thank you.